Thanks. I'll start from more of a perspective of somebody who uses machine learning to augment what we've traditionally done in computational material science as ways of computing properties of materials. And machine learning allows us to sort of extend that to much larger systems. So that's sort of the framework of this talk. And I start from a general introduction of the class of materials that we care to investigate. I was assuming there's a broad audience here, so I thought I would start with a lot of background of the material class that we're interested in. So the set of materials that we're interested in investigating are called transparent conducting oxides, and these are found in a variety of different optoelectronic devices. For example, a solar cell, shown here in this configuration, where light passes through some anode layer and is absorbed in the active layer of the device, where it's converted to free charges. Because this is a device, then you have two contacts, like a cathode and anode. And because light passes through this anode, it has to be transparent to the incoming light, or else that would be detrimental to the overall device efficiency. And if you just invert this device and instead are injecting charges and emitting light, then that's what we have in our laptops and cell phones. So this is a very common device structure that's found in a lot of places. And the material that is used in this anode layer typically is indium oxide. And that's because it has a nice compromise between having a large bandgap energy and a high conductivity. And the bandgap energy is an important indicator of transparency in the visible range in particular, which is where we're focused on because of photovoltaics or light-emitting applications. Because the bandgap energy shown here, the difference between the valence band and the conduction band in the material, if the bandgap energy was something like 2 eV, then it would couple with light and absorb light in the red or above. And so that would, of course, be detrimental to this device efficiency. So instead, what you need is a very large bandgap energy. That way, the light passes through and is not absorbed, so it's transparent to that. Typically, though, materials that have very large bandgaps are not conductive. For example, if we look at glass, these windows, it's made of typically silicon dioxide as the main component. Those have bandgaps. Those glass typically has a bandgap around 9 eV or so. And sorry, did somebody say something, or was that a sneeze? Oh, okay. But if you go touch it, then it doesn't shock you, so it's not conducting. So typically materials that have a very large bandgap are not conducting, but indium oxide is a special case here. And the problem with indium oxide, though, is the fact that it's difficult to process, and it's also something you don't go and mine out of the ground itself. It's actually a secondary component, so it can be quite expensive. And so it's often used, but it's limited in the supply. So one strategy in material science to sort of augment the demand of indium oxide is to start from something that's expensive and you alloy it with cheaper materials. And so the strategy here then is to typically you move up the row in the periodic table. So with indium oxide, its neighbors above is gallium and aluminum. These are cheaper materials, so you can alloy indium with those compounds instead. And that's what I'm showing here, where if you go up the group 3 oxides, gallium oxide has a bandgap around 5 eV, and aluminum oxide has a bandgap around 9 eV. And so what's interesting about this is that, in principle, if you were able to alloy these components together successfully, then you can have a large area, a large range of possible bandgap values that you can tune this material. That allows for not only applications in terms of optoelectronics, but also in other applications as an active material of a transistor. So with a very large bandgap energy, that leads to a high breakdown voltage, and so this is advantageous for specific applications. And so this is something that has been done successfully experimentally. People have alloyed these compounds together. It has tuned the bandgap over wide ranges, and at least in some older works, which I'm citing here. And this is something that we, in collaboration with some institutes in Berlin, have investigated. And the goal here is to try to identify what the stable materials were as a function of composition. What makes this problem very difficult is the fact that these compounds themselves, aluminum, gallium, and indium oxide, have different ground state structures. So if you were to alloy these compounds together, it's not clear at a given composition which structure would be adopted. And indeed, it's not even clear if it would be stable, if it would instead energetically prefer to decompose into these more stable states potentially. So from a computational perspective, we have to be able to estimate both the bandgap energy for its application, but also estimate, in this case, the stability. And so one way we can calculate the stability is quite simply, if we have some mixture, so A2B3, it's a combination of two elements here. We just compute the energy of that mixed material and subtract off the constituent elements, so A and B in this case. So by definition, these two limits here of pure A and pure B are 0. If the material it has a positive energy, then it's unstable. It will decompose into these lower energy states. If it has a negative energy, then it's stable. It's not sufficient to just look at one compound, though. This is why we need machine learning, and that's because the space to screen these materials to find the stable compounds is actually quite large. The reason is because we have to sample all of the relevant possible states. And for this case, when you talk about alloying materials, the relevant states are these configurational states. So I showed a cartoon here where the green, this is a unit cell of gallium oxide, and you have the green tetrahedral corresponds to one element, and the purple corresponds to another element. So these green colors indicate that we have different ways of decorating the lattice uniquely. Each one of these states has a correspondingly unique energy. So in order to find the minimum and the stable compound, you have to be able to sample this entire space, and that can grow to be quite large. So if you have a unit cell with 32 sites on it, then you're substituting 2 atoms, and potentially that's 2 to the 32 possible configurational states. So it's a very large space. And this is where machine learning can help us to screen this. And it's not just sufficient to look at one. So this is for one lattice, but also we have to look at all the relevant ones that have been reported, because it could be the case that once you start to alloy, that these other states might become favorable. So we have to repeat that same procedure for these additional polymorphs. So this is something that of course can be quite computationally daunting. And so this is why we can use machine learning. And one of the big steps in machine learning, I would say, for machine learning in terms of materials, is how to represent this 3-dimensional structure and all the relevant physics of that and the important aspects as something that can be inputted into a regression algorithm, so as a vector, for example. So this is something that a lot of people here have worked on. Matthias Rupp, Gabor has worked on this as well. So there are several off-the-shelf methods that can be used, in fact, to make this transformation possible. This makes it easier to do machine learning in materials, I would say, but it also makes the problem a little bit more complicated because it's unclear what the optimum model should be. You start from some set of model classes. You choose the regressor. You optimize the hyperparameters, and that's a very large space in order to navigate with just simply the single summary statistics, such as the average error. And so this is something so tuning a model is non-trivial for our field. And typically, I would say that what people do is they start from something that they're more comfortable with. So, something that's being developed. So at the Fritz-Haber-Institut, we used MBTR because Matthias Rupp was there. So that typically is how we sort of self-select for these different ways of using these different representations. And so eventually what I'll talk about is how to, I think, a better way of navigating that space. But first I want to mention, just to sort of illustrate this a bit more, of how to navigate this large model tuning space. We sort of offloaded this. We outsourced this to the internet in our department. So instead of having the machine learning department in our institute do that, we organized a Kaggle competition. So we made this data set of about 3,000 different structures for these ternary oxides, and here's some details about the different the data set. So the 6 different lattice types, the unit cell sizes range from 10 to 80 atoms, and we gave very limited information in terms of trying to accurately predict what the outcome should be. And that is that we only provided the lattice vectors and angles, so very simple descriptors of the 3D-dimensional box, the composition, the space group labels, and the geometries. And the evaluation here, because we care about transparent materials, is both the band gap energy and the formation energy. And you can see that, I'm not sure if anybody has gone to Kaggle a lot, but this is a quite low, I would say, prize for the Kaggle competitions. And that's because as an academic institute, we couldn't really put a lot of money for this kind of competition. There's no monetary value in the outcome of this. But still, having said that, although there was a small prize, we still had a huge turnout, I would say, with nearly 900 people who participated in this. And I think in being consistent with this, with the theme of this session, I think the using physical insights for machine learning was illustrated in this Kaggle competition. So of course we had almost 900 people participate, so we had a really large set of different models, but the winner of the competition developed a new representation for this field. So I'm showing here a table of the top 3 winners, which were the ones that were awarded money. These 2 here, so SOAP is something that Gabor has developed that's been around for a while. I would say that's probably the most well-used representation of materials in our field. And this one here, the chemical properties and bond order potential, is something that has been published in conjunction with this competition, but had been around and being developed for a while. So I would say this is something that was already in the works for a long time, whereas the N-gram is something that came about from this competition. I think it shows how some physical intuition can help give an advantage in training machine learning models. But I do want to mention that the top 4 models, really, in terms of standing out, the error metrics were pretty similar. So these were all basically equivalent in terms of their performance. So in the winning model of the competition that we organized was this N-gram model, and I think the idea here was quite clever. So the winner, this guy named Tony Y, he had the insight that the class of materials we wanted to investigate, these oxides, they have this well-defined coordination environment. So you can see this sort of as I colored it in the unit cell, but I also translated it here. So the atoms occupy these well-defined coordination environments where the number of neighbors is well-defined. And his insight was that these single entity coordination environments can be used as similar to a word in a sentence, like you would in an N-gram model. And so by having the complete list of possible unique coordination environments, that creates your sort of dictionary here that you can apply to the entire data set. And these coordination environments are generated just based on an indicator function iterating over these bond distances. If they're within a certain threshold, then you would say that that's, you count that in the coordination environment. So a very simple formula to actually generate these. And once you have the unigram, of course, you can combine the different ones based on contiguous sequences to build up the higher order bigram and trigrams. So effectively what he's done is he was able to translate what we would think about as a crystal structure, this unit cell representation of a crystal structure, into a crystalline graph instead. And so now that we have this representation, it's easy to build features from that. And in particular for the N-gram model, this is, so the nodes here in this crystal graph correspond to the unique coordination environments, and the edges between the graph correspond to the atoms that are within the coordination environment. So that's how this crystal graph is generated. And then once we have the crystal graph, of course, we can generate these histograms by counting the presence of the complete list of unigrams and bigrams and trigrams. And that was plugged into a kernel ridge regression method. So I think that's a pretty clever idea by being able to translate something that has been developed in a different field into material science. But taking advantage of this.
It's very much like the ECFD thing with NSPC and informatics, right?
Yeah.
But this was novel, though? This hadn't been done?
It hadn't been done, well, around the same time the competition was running, there was a paper by, I forget the first author, but the last author was Grossman, who used a graph-like representation combined with a convolutional neural network.
That's different than these kind of what we call fingerprints in the chemistry world, right? Where you're taking this fragment, this fragment, this fragment, and your fingerprints or things can
Still based on the coordination environment, or based on some?
In chemistry, we talk about bonds.
Bonds, yeah. But there's some radius of cutoff that you, yeah.
Effectively, that's going into action, but it seems closely related.
And then you also build the histogram from that, from counting? Okay, yeah, so very, very similar. But what's interesting and sort of simultaneously, I think, speaks to the point about trying to obtain a good model for your applications. The average errors, which I'm showing here for both the training and test for the formation energies and also for the band gap, since we cared about these 2 properties of stability and transparency. These 2 properties are proxies for stability and transparencies. What's interesting here is, of course, you have these really good, relatively good average errors, but you have these really large distributions of other errors. So there's generally a very uncertain sort of prediction in a huge portion of the space. And if we look, so if you just translate this scatter plot to a violin plot shown here, so this is the distribution for the training and the test sets showing side by side. And then I also compare the different models that were the top 2 and top 3 model here, so this BOP and the combined with a light gradient boosting machine and SOAP with a neural network. Then you can see that you can make some conclusions based on the overall sort of distribution being very distinct for these different combinations of representations and regressors. So we do see some sort of distinct sort of distribution here, and that is, so we started to play with this game a little bit and looked at how that pattern changed as a function of changing fixing the representation and changing the regressor. And you can see that predominantly the patterns now start to seemingly being dominated by the regressor here. And so what this brought to mind is if you look at the average errors, though, the average errors are all pretty similar, I mean, within 10%. And so you couldn't really draw some quantitative statement about which method would be better, although the distributions seem to be pretty distinct. So we're trying to rationalize and combine these two different ideas here about how to navigate a space based on the summary statistic, and also trying to figure out more of where these models are performing well and performing poorly. And so our idea was to treat this as a supervised learning problem. So we now train a model on the errors of the outputted initial model. And in contrast, so to sort of frame this a little bit more, in contrast to a global supervised learning problem where we try to fit some model to all samples in our space, to predict some target property. You could do that, of course, in this case with a Gaussian process regressor, but we don't really gain too much physical insight from this sort of model and this prediction, of course. So here it's just the model is going to be a linear combination of kernel functions. It doesn't really tell you much about what this underlying distribution should look like. And so our idea was to sacrifice a global prediction model and this entire space, and instead focus in on the more interesting points within this distribution of the errors. And for that, we turned to something I think was very similar to what was discussed yesterday in terms of the decision tree models. But we turned to an algorithm known as subgroup discovery. And so instead what we want to do here is focus in on these populations that display outstanding characteristics. So for example, in our target property, a population that might be a particularly low population. And so similar to what we heard already, the language here is quite similar to these decision trees. So we have a set of base propositions, and each of these propositions is simply some inequality constraint on some coordinate, some feature space. And then a selection language, so how do we identify these outstanding points here? It's just a conjunction combining these different propositions. So in this case, for this very simple example, this population can be identified by a single constraint on the feature space that we've introduced, this x-axis here. And this is identified by actually maximizing this objective function here. So we want to maximize these two terms, the coverage, the product between these two terms, the coverage and the effect on the target. So the coverage is the number of samples within this population, and the effect is going to be the shift of the average within this population versus the average over the overall space. And of course, so this is if we just do it for a one-dimensional case, but if we want to identify, for example, this population here, if we introduce a second set of descriptive features, now we have labels for these different points, so some are circles and some are squares, then we can identify this population based on a constraint on x1, as well and a constraint on the category of the points. And so this is the idea where we want to sacrifice the global prediction and instead focus on locality, and I think this is why this algorithm should give us an advantage in that. And so just to sort of, that was a generalized picture of it in terms of abstract wise, but to illustrate it a bit further for prediction of errors here, I want to show a few toy examples. So we generated this two-dimensional plot using each axis was generated just as a normal distribution, and then we generated the target properties here. These would be our errors as just this third-order polynomial in the x direction, the x1 direction, and with an increasingly large noise in the x2 direction that goes as the exponential of x2 over 2. And so if we just fit a model to this, something that can't quite capture the complexity of the underlying distribution here. So here we have just a simple linearized kernel ridge regression method here. Then as you deviate from this midway point of x1, you get more nonlinearity in this equation, of course, and this plane cannot capture that complexity. So you have very high errors then. But we can still define a point where our poor model actually describes some points very accurately, and that's around where x1 is 0. And so this is this idea of the domain of applicability, which also comes from that term comes from the cheminformatics field. And so here we can define it just based on the constraint on x1, so a narrow window around x1. And here's a histogram showing, this is a probability showing that the global mean here is reduced significantly within this domain of applicability. Of course, this is at a sacrifice of a lot of points. And to sort of contrast this with another example, where if we now train a model that has the sort of correct complexity in general, so this is a polynomial kernel, third order, so it should capture the complexity at least in x1, but because the noise term in the x2, it can't capture that, we now can identify a domain of applicability within this direction here. And so we have other examples of this, but I think this shows that how the concept of how we want to apply this domain of applicability in terms of understanding the locality of error distributions. And this is a way of understanding, I would say, uncertainties in your predictions, and going beyond. I think a speaker on Tuesday made a good point where he said that a problem with using, I think, SOAP and GPRs in that case is that it makes point-by-point uncertainties, analyzes the uncertainties point by point. So it gives you a point-by-point estimate, whereas this gives you a sort of interpretable descriptor about where your model performs well. And from that physically interpretable descriptor, hopefully you can infer why that's the case. And so to do that, to come up with a language that would allow us to analyze sort of the model problems and problem points here, we have to introduce a neutral representation. And so the idea is to sort of apply this to understand where the representation step, so how do we represent different materials, leads to these intrinsic biases in the predictions. And so to do that, we could, of course, input the actual features from the models themselves, but instead, if we want to do a side-by-side comparison, we have to have something that's a bit more neutral. So in this case, we just came up with a very simple set of features here. That is the unit cell structure itself, so the different axes of defining the unit cell box, and their angles. So this gives you an indication of how distorted the box might be, as well as the volume of unit cell and the number of atoms contained in that. So this gives you an idea if your model can apply to different sizes. As well as, for our specific case, we have these 3 different atom types, so we thought we should include that. And we also give some local information in terms of the structure. So here it's just the bond distance of the average nearest neighbors. So in this case, if we have the 6-coordinate environment, we would just average over these 6 different atom types, excuse me. And the motivation for choosing something that gives you a little bit more of a local information of the structure is because of the fact that all these representations start from essentially a sum over different bond distances that is either input into a histogram in the case of MBTR or transformed in other ways. So this is sort of underlying crucial step in building these representations of materials. In terms of the application of this, we applied it to it's the same Kaggle data set, but we use different methods to give more of an even side-by-side comparison. So here we regenerated the predictions using 3 representations. MBTR, this is something Matthias has developed at the Fritz-Haber-Institut. SOAP, of course, is from Gabor's group. That's the sort of the benchmark method in the field. And then the n-gram one that won the competition, at the Kaggle competition. So this is for the same data set. And on the right, what I'm showing is the global distribution, this violin plot. And on the left is what I'm showing, these different domains of applicability that are identified for these different representations. And this is all based on building a model from the representation plus this kernel ridge regression using the Gaussian kernel. And here I'm showing the absolute error, but actually the target was a relative error. And that's because it's less correlated actually with the target property than the absolute error. So that's sort of a choice that allows us to actually sense more of the differences between the methods as opposed to incorporating something that's correlated with the target property. So the summary of this result is shown here in this table. So for the 3 different representations that we have, This is the global result, so you can see that it compares very similarly. Whereas within this domain of applicability, we have something about a factor of 2 lower for the MBTR, and similar, and for the other decreases for SOAP and Ngram. And what's interesting is that, of course, that the descriptor we've optimized that defines these different domains is qualitatively very different. So for the MBTR, it incorporates this n atoms, and as well as other parameters based on the shape of the unit cell, so the angle here. Whereas SOAP has this ratio between these two, the longest and shortest lattice vectors, and constraints on the unit cell itself. So this indicates that SOAP does better for more symmetric unit cells, for example, whereas MBTR does better for unit cells of a one specific size. And so on. So we can sort of start to infer exactly why these methods perform how they do based on the underlying assumptions made. So for example, in this case with SOAP, what's interesting there is the fact that you tend to have to define a cutoff radius a priori. And so what that seems to do, at least for this case in our data set, is introduce a bias against unit cells that are not symmetric. So so this is sort of a summary for the overall data set itself, but we can also play a different game where we can tune. It's a bicritical optimization. We have this product between the coverage and the effect that we're trying to optimize. And so you can effectively weight the coverage by hand here. And that's what you're seeing in this plot, where I show for these 3 different models how they evolve with the relative area, how it evolves with the different coverages. And so although the optimal solution for SOAP using a equal weighting between these 2 terms gave something around here, actually you can see that the error distribution for SOAP is very good across the entire range of coverages, whereas methods like MBTR increase quite steeply. And surprisingly, for whatever reason, the Ngram model does very well for a very, very small population here. And so these are the sort of details that we're trying to be able to access when we're decided to go down this route of using subgroup discovery, ways of sort of inferring different results from the representation and how the representation can actually affect the overall error distribution. So I have some time left, but I want to sort of switch gears to a different application that uses physical insights. And for about 10 minutes before doing that, I wanted to see if there are any questions before I sort of moved on to a different, yeah.
So these different descriptors have different degrees of user settable parameters. Do you have a sense of how these results that you're showing, how do they change? What changes evolve?
Yeah, with SOAP, we did that by hand. What we did is we modified this cutoff value that's set. And you saw that basically that value became related to the distance of the lattice parameters. So if you change it from 10 angstroms to 20 angstroms, then you include the next sort of unit cell image, and the selector changes as a result of that.
Have you tried this sort of cutoff-free version where you average the spherical coefficient before you square?
No, we didn't.
So that, I think for crystals, that's sort of what
yeah. Yeah, but I think what was interesting for us is just to see the sort of feedback between the parameters that you tune and the selector that's identified to the error distribution, and just getting a handle. I mean, this is certainly early work. I don't mean to suggest that we identified some fundamental flaw, but it's just a matter of.
But it's interesting to see how the different parameters.
But we can start playing this game of exactly, what is the method missing, and. Or is there a way of sort of improving this in some way? Or does that make a difference whatsoever?
Because this would be guidance to people using this.
That's exactly right. Yeah, that's our hope. Yeah.
Which is very empirical.
It's empirical.
Worse than empirical.
It's worse than empirical. Yeah. I mean, how do you even? I mean, you start from some method off the shelf. You say, okay, I like SOAP. SOAP's done well for me in the past. Let me just sort of work with that a little bit, and you confine yourself to just that method essentially. It's really hard, I think it's really hard to tune all the hyperparameters and of the different model classes with the different representations. It's a very large space to navigate. And at the end of the day, as we saw in the Kaggle competition, the average errors are basically the same. So what's the point? if you're just trying to do that. So I think instead here, I mean, there are other implications. We haven't quite figured this out how to do it yet, but the natural extension of this is sort of ensembling. If we see that there is a very distinct pattern in terms of where these models are performing, then we should be able to combine that in some clever way, although we haven't quite got there yet.
Are the error levels within these domains of applicability actually predictive?
Oh, yeah, thank you for bringing that up. I forgot to mention, yeah. So we actually set this internal boundary. So for this data set, this bar here is the average error between the two minimum structures. So the difference between the two minimum structures. So if you are below this, in principle, you could distinguish between those two structures in our data set. So you could find the ground state is what this represents. And so that's actually an interesting result for MBTR. You have this, for 44% of the data set, you still have this very good description. The entire distribution is below that, right? So did you?
So that sort of tells you what the relevant error scale is. But I do a bunch of tests. I get an error landscape. I use this procedure to identify the domain of applicability. Right? If I then generated more test points within one of those domains of applicability, do I have reason to think that the expected error will actually match the error that I measured so far? Basically, are these error landscapes smooth on the length scale of the domain of applicability?
Yeah, I mean, I think there are several ways to go here with this idea of is the error converged within the domain? Right, like if you add.
Well, how did you determine those? Is it on a Howdell set?
Is
it on a whole?
Yeah, that's another point. This is actually done through this sort of. I don't have a slide on that, but we took the test set, we split it into a training and a DA identification and DA validation partition. So we trained this on a DA identification, and then the numbers here are reported on the DA validation set. So it's a strictly holdout set. Since we're doing a supervised learning on the training sample or the test samples, then we have a second holdout set here that the model has not seen. So these are not optimistic estimates of the error.
That would suggest that the answer is yes. Right?
Yeah, exactly.
So
But
basically, you're saying that the plot on the next slide will depend a lot on what your test data is. If it's different, the plot will change. But if you have a completely different set of test points, you won't get the same distribution.
I think that the certainly in our data set, there's a well-defined sort of structure, especially in terms of N atoms, for example. And so I think that you mean qualitatively for the selector or just the errors?
Just the distribution of the lines, the curves that you saw on the next slide.
How will this change?
Yeah, the coverage and the error, that will change based on what points point you're. I mean, this is averaged over the DA validation set, so the unseen data. Yes, I was saying if you have a different set of points and if the distribution is not the same as what you said, you might not get exactly the same curves.
Yeah, this is on unseen data, but.
If the distribution changes, sure.
Yeah.
But if it's the same, then this is an estimate of the error that you could get.
Right.
But if it changes, always. And we would put some new structures in, sure. But you would
what I
notice
meant was
that
if you're solving different problems using the same representation, it depends. Let's say I'm solving a problem on lithium silicon data set versus something else. I can't say because MBTR gave me the best error and coverage for one problem, it will give me the best for the other problem as well.
Yeah, no, I think it has to be adapted to a specific, modifying the target as well. I mean, in principle, in our case, for this specific example, I'm doing the relative error, the normalized absolute error, because we want to sort of see the differences between the models, how they predict. But I mean, in principle, hypothetically, you would want to actually preserve your error for the points closest to the convex hull in this application space. And so that should be, you could come up with a sum between your sort of the target in some way and the error. as a way of confining your domain of applicability to the place, preserving your error where you really, really want it effectively. Right. I mean, so I think there's several things you could modify here for a specific application.
I suggest if you have another application that.
Oh, I could stop here. I mean,
No, you have a little bit of time. Like.
I'm happy to discuss this more. If people,
Okay. Yeah.
how much more time do I have?
5 minutes.
Oh, no, it's fine. I don't have to talk, but I can stop here. It's good.
No, you still have time, right? I mean, it's 3:15, so and then so if you go to.
I would rather, stop a little bit early than rush through the second part, because I think that would just.
There's one aspect, if we want to discuss, we could come back to what Patrick said about the similarity to the fingerprints. I think there is an aspect of your data that you haven't mentioned in the summary, but that might be important here, because if I remember right, the Kaggle data was such that the energy that is predicted was from the relaxed structure, but the actual
Right, that's
given
right.
structure.
That's right. So, so one motivation for coming up with a Kaggle data set, besides the idea that it's specific for a case that we cared about, our collaborators in particular, was the fact that most data sets you find in terms of the benchmark data sets that are available are generated on relaxed structures. And that's not very effective or useful at all for trying to do high throughput screening. And so this data set was generated with these sort of what are called Vegard's law geometries, where we take the average geometry between the three constituents and to generate it. So it's trivially generated, and you can make the prediction from that. So those are the structures that we use for the Kaggle competition, since they're useful for high throughput screening. But your point is that you can look at the difference there.
So now,
The question is, does the relaxation change that graph in the n-gram? Because you can imagine the relaxation chart moves everything around, but if all the coordination environments are the same, then the n-gram doesn't take care.
so
That's a good point. Yeah, no, I mean, I didn't think about it in terms of, I've looked at it only for the MBTR one, but I didn't think about it for the,
Is the distance exactly where the n-gram?
that also uses this, so SOAP uses distances, but SOAP is a bit more flexible in the distances. I think because MBTR, you have this sort of dampening function. I think that kind of, anyways, but.
this is exactly why I brought this up.
No, that's a good point. I didn't think about it in terms of the n-gram, but I think that, yeah.
Right? This is the reason why you measure, basically this is noise on the inputs, right?
Yeah, absolutely. That's right.
Structures have noise.
Yeah.
And then something that is somehow a bit resistant to that noise because it doesn't model exactly like this n-gram can work.
Right.
Yeah.
But we tested it. I haven't tested it for n-gram. I have tested it for MBTR, of course, because of you being there. And we see the same selector between MBTR on the relaxed and the, yeah. So we see, so there it didn't change because you still have that sort of heterogeneity within the data. And I think MBTR really preferences that when you do not just the representation, but then when you do the regression part, it really sort of finds that group.
So we looked at this relaxation issue on GDP now, and it makes a huge difference.
Yeah.
The way to what you can do, and which still takes this into account and makes it still useful, is that in the input data, in the training data, you know how much the relaxation
Right.
is because you actually relax it to get
I
the
see.
training data. And if you take the distance between the unrelaxed and relaxed structures in configuration space and use that in your regression as an indicator of noise in the KRR, this is easy, right? It's just that you write that number on the diagonal of your regularizer. So this is, for the ordinary KRR, the regularizer is a scale, but in the regular view it isn't. And so you take your diagonal regularizer of the diagonal elements, you write something that's proportional to the distance. That gives you a factor of 2 by and that's really
Interesting.
and anytime this inhomogeneous, and what happens essentially is that there's some data points where the relaxation is large.
Yeah, exactly.
And they will really screw up your fit unless you let the model be a loose error at them. You're not going to, right? Essentially, that's what's going on. Is that the diagonal term in your KRR for those configurations will have a larger diagonal term, so it's like downgrading them in your linear.
In your model, at least, yeah.
And so for the rest of the model, you're not.
And so you just assume that would then be better, more generalizable to the
Exactly.
to the data set that's not
effect
okay.
is pretty significant. It's pretty significant. It's very easy to implement.
Yeah, sure.
Flash by a few conclusion or
Oh, sure. Yeah, I mean,
just to kind of
close it. You mean?
close it and
For
then
sure.
we can move into discussion.
Serious one.
We're not,
Is this the last factor too?
Well, I think I'll skip ahead to the acknowledgements then. That's the most important part. Okay. Yeah. So I didn't get to the right-hand part. So just my colleagues. Mario Boley is a co-author in that paper, and it really is a developer of this subgroup discovery method, and came up with the idea of trying to apply this to these test set predictions. That has led, I think, to very fruitful work, along with all these different other colleagues, Matthias Rupp in particular, and my colleagues back in Berlin at the Fritz-Haber-Institut. With that, I'd like to thank you for your attention.